Hey, welcome back. This is the last section in trig that we need to cover. And again, it's associated with vectors. Okay, so in particular, when we looked at vectors last time, we didn't really have this idea of multiplication. We had the idea of addition. So, you would have something like u plus w. You had an idea of subtraction, so u minus w. There was also scalar multiplication. So we could take a vector and multiply it by any number we wished. So maybe like 5 times u. And but it wasn't really truly a vector times a vector. Okay, so today what we're going to do is introduce one of these vector times vector operations. And this type of product we're going to call the dot product. It turns out there's actually two versions, but we're mostly just going to work with the dot product and then leave the other one for your physics class or your later calculus type classes. Okay, so what is the dot product? The dot product will turn out to just be a scalar number, like the multiple in here. So you're going to take two vectors and combine them together, and somehow it outputs a scalar. What I think of with this dot product is kind of like, I wouldn't say it's like a slope, but it's like a numerical measurement between the alignment of the vectors. Okay, so first to indicate a dot product, what does it look like? You're going to put a little dot between the two vectors. Okay, so this would be read u dot v. Okay. So again, what I think of it is as a measurement between the alignment of the vectors. So if this was u and this is v, they're kind of almost going in the same direction. Okay, so that dot product u dot v would be greater than a dot product if they were orthogonal, which means perpendicular. Okay, so in this orientation, you would think they're completely out of alignment. They're kind of working against each other somehow. So in this alignment, maybe we should call these two other vectors w, and then we'll call this other guy vector, I guess, s. Okay. So u dot v would be greater than w dot s. Okay, and that's the way kind of I was introduced to it, and the book doesn't talk too much about that, but that's kind of how I would think of these things. It's helped me a lot going through some of my physics classes when I was first starting, and then later on when I studied more things like vector calculus. Okay. Okay, so anyways, let's go in and now kind of get along with the book, what the book is doing, and kind of go along and make this a little more rigorous. Okay, so section 1, first they're going to note that the dot product will give you not another vector. So in that way, it's kind of not like a true product still. The other product that we don't talk about will be a combination of two vectors that gives you another vector. So that's more like a traditional multiplication. But anyways, dot product is not quite there. The dot product will result in a scalar. Okay. So a dot product is not really a vector. It'll turn into just a regular number like we're used to. So anyways, here's checkpoint 1 from the book. Just, what the heck are we doing? They'll give you two vectors, and they want you to determine the dot products. Okay, so the first vector, 7i minus 4j, and then this vector w is 2i minus j. Okay, so part A, they want v dot w. And it turns out to be pretty easy. All you have to do is multiply the first components together, okay, the coefficients of the I vector. So you'll have 7 times 2. And then you just add in the and you could probably guess, right? It's just add in the product of the j component, the coefficients of the j vectors. So -4 times -1 in this case. Because if you don't see anything in front, you just pretend there's a 1 there, right? Okay. Okay, and then you just add them together. I got 14 plus 4, which is 18. And that's it. Okay, so it's pretty simple. Let's look at this next one. W dot V. Okay. So in this case, I first begin with the 2 and then times 7. Okay. So we'll have 2 times 7. And then add in the product of, this time, -1 times -4. Are you going to get the same answer? Let's see. I got 14 plus, yeah. Because of the commutativity of multiplication, the dot product is also commutative, right? And I think I remember the word commutative because of commute. You're going back and forth. So v dot w is the same as w dot v. You can go back and forth, okay? So there's going to be a lot of properties of the dot product. I'm not going to list them out. They're listed in the book on page 786. Okay, so see page 786 for the complete list of properties of dot products. And you can explore those details in more depth. Basically, you use those properties to produce these other formulas that we'll need through this section. So there's going to be a projection formula that we need, and there's going to be a work formula from physics that we'll need. So in producing those formulas, we use the properties of dot products. And we also use it in order to do a proof of this other formula for the angle between vectors. Okay. But before we get there, let's look at the last part in checkpoint 1. What is W dotted with W? Okay. Well, W dotted with W is just going to be you take the first component and dot it with the. So if you wanted to write it, you could write it as 2I minus j dotted with 2I minus j. Okay. So for the first term, it would be 2 times 2, which is 4, and then you're always adding. Okay, and then plus -1 times -1 is 1, okay, which turns out to be 5. One weird thing about this is it may look kind of familiar. It's similar to the magnitude of W. If you remember the magnitude of W, that was the square root of the component squared. So in this case, it would be you take the 2 and you square it, and then you add in the -1, you square that, right? So it looks a lot similar. And in fact, when we do our first kind of explanation of our first formula, you'll see that. Okay, we'll have to use this fact. Okay, so it's, what is it, 4 plus 1, right? So the difference between W dot W and the magnitude of W is just 1 is squared. So we can write that, and that turns out to be one of the properties. Hold on, I got a student. I'm sorry about that. Okay. So where are we? Oh yeah, so there's an obvious relationship between, and this is one of the properties. You'll see this in the book. It's property number 4 in this list. So property 4 says, and like I said, I'm not going to write them all out. Let's just write this one. I think it'll help in the next kind of discussion. So property 4, we note that basically if you take W dot W and you can make that you can make it equal to the square of the magnitude of W. Okay, so because if you square it, then you'll get rid of the square root, and you'll have the square root squared, and that'll get rid of So you'll just end up with 5. Okay. So what we're going to do first with the dot product is kind of connect it, and in this way it's kind of connected to this idea up at the top of the screen where I started today. It's about the alignment of the vectors. Okay, in particular, a formula, we can obtain a formula for the angle between two vectors that's connected in a weird sort of way to the dot product. Okay, and the formula is kind of awkward when you first see it, but hopefully you see it here, and by the time you get to physics or later vector calculus, it won't be too crazy. So it's, why were we doing all that stuff with solving the triangles? It's part of that stuff material is applied here when we're developing the formula for the angle between two vectors. Okay. So in particular, you could take two vectors like this, and sorry, they're actually at any angle, theta. They don't have to be, this looks like I made them 90 degrees. I didn't mean to do that. But then you could consider this other vector over here, call it like vector u. So let's put some names on these. This will be v, this will be w, and this will be u. And what do you have at the end of the day? You have a triangle, okay? An oblique triangle like we had before. And we could produce a formula for theta. At least a formula that incorporates theta, right? So you'll have the magnitude of u squared will be equal to the magnitude of v squared plus the, because, it's like that a squared plus b squared. A squared equals b squared plus c squared minus 2 ac cosine of the angle across from u. Okay. So anyways, v squared plus w squared minus 2 times the magnitude of v times the magnitude of w cosine theta. Okay, and then this is, I'm going to kind of cheat a little just because I noted this property back here. Okay, I don't want to write out the entire description here, what's going on. It's in the book, but hopefully if you're willing to accept property 4, then hopefully you'll be willing to accept there's some manipulations we could do, and we end up with v dot w equaling the magnitude of v times the magnitude of w times cosine theta. Okay, if you don't believe me, you can read in the book, but it really hinges on this property here, that we're able to do some replacements with dot products in place of the magnitude squared. Okay, so you go yada 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 and all this region, and we end up with this formula, and then you could solve this formula for cosine theta, and that will be our first formula. Hence we get cosine theta equaling v dot w all over the magnitude of v times the magnitude of w. Okay, and so anyways, what I was talking about at the beginning of the lecture about alignment between vectors, and I'll come back to this point again here in a sec, but you could see the dot product here is dependent on the cosine of the angle between the vectors. So it does seem at least plausible, okay, there is some connection between that angle, in other words, the alignment between the vectors and the dot product. Okay. Let's look at a problem from the book, right? So I think it's number 19, but okay, I'll just write number 19. Okay, so number 19. And what the book wants you to do is find the angle between the vectors. And they give you a vector v is negative 3i plus 2j, and then a vector w is 4i minus j. Okay, so it's just plug and chug really at this point. You're going cosine of theta. First you do the dot product, so v dot w. You're going to get negative 3 times 4 is negative 12 plus 2 times negative 1, which will be negative 2. 2 times negative 1 is negative 2, yes. Okay, and then downstairs you have to do the magnitude of v. So you got the square root of the component squared. So negative 3 squared is 9, plus 2 squared is 4, times the magnitude of w, and you take the square root of 4 squared is 16, plus negative 1 squared is just 1. Okay. And then we're going to simplify all that material. We get cosine of theta equals negative 14, all over the square root of 13 times the square root of 17. And you can, I guess, rewrite that. Let's write cosine of theta equals negative 14 all over the square root of 221. Anyways, I'm going to go to the calculator, and I just, I do cosine inverse on both sides. And I end up with theta equaling approximately 160 degrees. So the angle between them is actually quite large. Okay, so getting back to this idea of alignment then, the alignment between the vectors. You could actually tell by the dot product if they are parallel or perpendicular. Okay. In this case above, we had something greater than 90, and when that happens, you're going to get something that an output that's negative. Okay, it's almost like they're kind of going in opposite directions when the dot product is negative. But anyways, the book will present it as noting that the vectors are parallel, and I don't know how to spell parallel apparently. So I'm just gonna write the railroad tracks for parallel rather than embarrass myself, and the upside down T for perpendicular, which they also call orthogonal. Orthogonal is the same for perpendicular. Okay. Right. So there are 3 basic cases. If they're going in the same direction, if they're completely in the same direction, the angle theta between the two will be 0. Okay. So maybe I have one vector u and then one vector v on top of it, like this, and then theta will be 0. Okay. So we kind of look at what happens to our formula for the cosine of theta, which is with regards to like the dot product, right? So let me rewrite the dot product above here. So u dot v we had from above. This is the formula I want to kind of look at right now. Okay. Equals the magnitude of u times the magnitude of v cosine of the angle between them. Okay. So in this first case, you have u dot v equals magnitude u times magnitude v of the cosine of 0. Okay. Cosine of 0, that's the biggest cosine can be. Cosine is equal to 1 in that case. Okay, so this will be just the product of the magnitudes. Whoops, times 1. So that would just be u times v. All right, the case when they're completely going in the opposite direction, you're going to get a huge negative number. Okay, so let's say this is u and then this guy is v. Okay, and theta in this case is 180. Okay, so in this case, u dot v will equal the magnitude of u times the magnitude of v times the cosine of 180, which of course is negative 1. So this is just equal to negative magnitude u times magnitude v. Okay, so they're completely out of alignment, so you get a huge negative number. If they are perpendicular to each other, or orthogonal, as they're saying now, so there's a 90-degree angle in between the two, then what do you think the dot product is? Well, exactly in between these two for 0 and the 180. It's just going to be 0, right? You'll have the magnitude of u times the magnitude of v times cosine of 90, and the cosine of 90 is just 0. So you'll get 0. And that becomes then a kind of a test for determining if the vectors are perpendicular to each other. So they'll give you a bunch of questions like that. Let's dive in there. Use the dot product to determine if the vectors are orthogonal. Okay, so let's take a look at 26. And they give us the vector v is 8I minus 4j, and the vector w is negative 6I minus 12j. Okay, so basically just take the dot product, and if the dot product is 0, they're orthogonal. In other words, otherwise they're not. Okay, so let's take a look. W dot v. And again, this is pretty simple. You just have 8 times negative 6 is your first term. So it'll be negative 48. And then plus, the second term is negative 4 times negative 12. Okay? So that'll be 48. Oh, yeah. And then negative 48 and 48 is 0. So those guys are orthogonal. So you can write our implication arrow, therefore, orthogonal. Okay, I'll just write I know what that means. You know what that means. Okay. Let's try another one. So v is equal to 3I, and then w is equal to negative 4j. Well, just looking at the picture of these, they should be orthogonal, right? So 3I is basically just on the x-axis, and then negative 4I is on the negative y-axis, 2, 3, 4. It's just this vector here. Right? So it should better be 0. Okay, so let's see, v dot w. You know, you sort of have to use your imagination for the other components, right? So this is 0I minus 4j. So we got 3 times 0, which is 0, plus 0 times negative 4, which is 0, and of course it's 0. Okay, so those are orthogonal. Okay, moving on. We want to kind of decompose vectors into two components, the component parallel to the x-axis and the component perpendicular to the x-axis. In order to pull this off, we do projections. We work with these things called projections. Okay? You can kind of think of the projection as a shadow of the vector. Projections. We'll use these when we work with physics in particular, and we'll develop a formula for work here at the end of this section. Okay. So first off, the actual formula itself, and this is no easy task to get this formula, and I'll go through it in way more detail than is probably needed, as opposed to the kind of yada 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 thing I did with the angle between two vectors. Okay, so the formula. First off, let's just look at a picture, right? Never mind the formula. So here's some random vector v. Okay, and my mouse just kind of flipped out on me. And then the vector v, if you draw this kind of line that's parallel to the x-axis, you can talk about an angle theta between v and this parallel line here to the x-axis. The projection of v is kind of like the shadow of v onto that axis. So it's kind of like the component of v going in the direction of the x-axis. Okay, so the projection will be that vector there, and we'll call it projection of v onto this other axis, w. So you don't necessarily even need to have, I guess, this w vector being parallel to the x-axis. You could rotate this entire picture, but I guess just for simplicity, we'll consider w to be parallel to the x-axis. Okay, you want my little vector arrows there. So it's the projection of v onto the w-axis. You could kind of think of it as a shadow. All right. And there's two parts to it. There's this part, the projection, and then later we'll talk about the components. So, you know, this part and then this part here as well. but we'll get to that other part here in a sec. Let's just focus in on the projection, right? Okay, so how do I get a formula for the projection of V onto W? First, I'm going to resize W so it has a unit length. And then I can kind of attach to it a scalar that'll give it any length I want. So I'll be able to resize W to kind of have the same length as the projection. Okay, so I probably kind of botched the original explanation. I want basically, yeah, if you allow me to, let me read, you don't have to, I'm going to redraw the picture because I kind of botched the explanation, the opening here. So again, what am I dealing with? I have this vector V kind of floating around in a plane, and I'm just going to project it. This is where I kind of made the mistake. I kind of think of this as a big, long, it's just another vector in some other direction. So this is a V vector. This is just any W vector you want, and then the projection of V onto W will be kind of like part of the W vector. So this red vector here would be the projection vector. Okay. Let me move that little symbol for W. I'm sorry, I know that if I could edit better, I would go and edit the video down at this point, but I can't because I'm not great at videos. Okay, so anyways, this red vector here is the projection of V onto W. Hopefully that makes sense. So the projection of V onto W. Okay, you kind of, I kind of butchered that letter J. So let me rewrite it. There you go. Okay. So we want to get a formula for the projection of V onto W. And what I said first is we're going to resize the vector W to have unit length 1. And we know how to do that from the previous section. And let's call it vector U now. And it will be W, the W vector all over the magnitude of W. Okay, what that does is kind of clean the magnitude of W, and then you can just multiply it by a vector, and you'll get, multiply it by a scalar, so some real number, and then you can get the actual value of the projection. So right now W, U is probably like this length right here. It's going in the same direction of W, but it has magnitude of 1. Magnitude of U is 1. And then we're hoping to multiply it by some scalar, C, such that then this thing will kind of go in the, so C times this new vector, this unit vector, which is actually W, right? And then this thing will be the projection vector. Okay. So what we need to do is to figure out this C value. I need to get this guy figured out. Okay, so back to, first I resize the vector, and then what the heck is the length of the projection vector? That's the C value that I'm kind of after. Okay. Well, I can get that using a little bit of trig, right? So if I consider the angle between the two vectors, W and V, and then take the cosine of that angle, so what I'm looking for is to find that C value such that C times this U from step 1 is equal to the projection of V onto W. Okay. So anyways, as promised, I'm using this angle theta. So note the cosine of that angle theta, so I note the cosine of theta is equal to adjacent, so the length of the projection of V onto U all over the hypotenuse, which is the magnitude of V. Okay. So you can solve for the magnitude of the projection, which is the C value that we're after. So the magnitude of the projection of V onto U is equal to the magnitude of v times cosine theta. Then we can take advantage of what we know about dot products to rewrite that formula there. So I also note then, because in this case it's v dot w, because v dot w equals the magnitude of w times the magnitude of v cosine theta. The projection of u onto v is just u dot v divided by w, the magnitude of w. So you can say then the magnitude of v cosine theta will equal v dot w divided by this magnitude of w. Okay, almost there. Okay, all this is that c value that we wanted. In order to, we're going to multiply that onto, do scalar multiplication onto this vector u. Okay. So thirdly then, finally, we create our new vector, this projection of v onto w. It will equal this value from sort of our step 2 here. That's the c value, the length of the projection, times the, and I don't want to put a little multiplication symbol because multiplication is now different, and times this vector u, which is w all over the magnitude of w. Okay, so times w all over the magnitude of w. And then the way they generally will write this is to multiply the two magnitudes of w's in the denominator together to produce this scalar v dot w all over the magnitude of w squared. Okay, so that then becomes the official formula. For the projection. Okay, so hopefully some of that made sense. It's a bit of fancy footwork. The more experience you get with vectors, though, if you didn't understand it, don't worry. The more experience you get with it, it's like, oh, that's no big deal. Okay. Okay, so anyways, there's that. Let's get back to the homework then and see what kind of problems they want us to deal with. First off, here in this 34 problem, they want you to find the projection. So find the projection of v onto w. And then they give us our vectors. V is 3i minus 2j. And then w is 2i plus j. All right. All right. So what do I need? I need the dot product. Projection of v on the w is going to be the dot product of these two, so 3 times 2 is 6, negative 2 times 1 plus negative 2, all over some magnitude. So we got the magnitude of first v, whoops, it's just w squared, sorry. So, and then when you square it, the square root will go away, but we'll write it in all of its glory. It's the magnitude of w. So the first component squared is 4, plus the second component squared is 1, and then you have to square that, okay? And that will get rid of the square root. And then times the vector w. So 2i plus j here. 6 plus negative 2 is 4, all over square root of 5 squared is just going to be 5. And this is a scalar times vector, so you just kind of distribute the scalar, and you end up with 8/5 I plus 4/5 j. Okay, now the second part is that other component. So the red vector is kind of considered the first component. We want to, it's called decomposing the vector. We want to find this other vector here. Okay, So we'll call this projection vector is traditionally v1, and I guess this other vector will be v2, right? All right. So how do we pull that off? And you can kind of see from the diagram how it'll work. Basically, well, if you remember, addition of vectors, how do you do that? You place some tail end, if you have one vector and you want to add it to this vector, all you have to do is take the second vector and kind of plop it at the end of the first vector, and then that length there is the sum of the vectors, right? So v, and then if this was w, to add them together, you just put them end to end. So this would be v plus w. Okay, so over to the other picture then, we can see that v must be equal to v1 plus v2. And it decomposes then this v into these other two vectors. Okay, so let's kind of make that a little more clear that we're looking for the components of these of this particular vector v. So we have some vector here, and how do we get that? We're going to first get v1, which is actually just a projection of v onto w, and then we'll get v2, and to get v2, all we have to do is kind of solve this equation for v2. So if you solve for v2, it'll be v1, or sorry, just v minus v1. And they should all be vectors. V minus v1. Okay. Okay, so let's try one of these exercises from the book. We'll try 36. And let's make 36 also the video quiz for the day. And let me write that in my notes. This will be the last video quiz we have to do for the class. And it's in homework number 5. Did I say the last one is it? Okay, so homework number 5 is going to have 3 sections in it. Hopefully I didn't accidentally say it only had 2 sections, but it includes 6.7. So this is the last question in homework 5, and it's actually problem 36 in the book, where we're looking for the components v1 and v2. And I will give you the vectors as soon as I copy it down in my notes. So what do we have then? Problem 36, v is 2I plus 4j, and then w is negative 3I plus 6j. So we want to find v1 and v2. So v1, first off, is just the projection vector. Okay? So v1 is going to be v dot w. So I get 2 times negative 3 is negative 6, plus 4 times 6 is 24, all over the magnitude of w squared, which will just end up being getting rid of the square root part, right? So it would be 9 plus 36. And that will be kind of the constant, the scalar multiple of the vector w, which we already know is negative 3i plus 6j. Okay, so let's figure this out. Negative 6 plus 24 is 18, all over 45. Okay. And then simplify that, looks like 2/5, and then distribute. Okay. Okay, and then to get v2, you just take the difference of v and v1. Oops, and these are both vectors. So v minus v1, we have these vectors recorded already. It's 2i plus 4j minus negative 6/5 I plus 12/5 j. So this will equal finding common denominators. I guess I got to do that. So this would be 10/5 I plus 20/5 j minus negative 6/5 I plus 12/5 j. 10/5 minus 6/5 is 4/5 I, and then 20/5. Wait a second, it would be plus because I have to distribute my negative. So that first one is actually 10/5 plus 6/5, which is 16/5. Sorry. And then the second guy, 20/5 minus 12/5 is 8/5. Okay. And that's it. Those are the two components of vector v. Okay. And in physics, they'll kind of decompose velocity of objects into their vertical components and horizontal components and work that way. All right. So it's important in physics. So speaking of physics, then let's talk about work. Okay. So it's kind of exactly what you think it is. It's a measure of a force over a certain distance. So imagine I have this box, and maybe if you've ever seen the strongman competitions, people are pulling trains and things like that. It's just crazy. But you imagine this person is pulling this box, so they're exerting a force in this direction, and they're going from point P to point Q. Okay. The work is going to be the force, the magnitude of the force times the distance. Okay, so it's the magnitude or the amount of force times the distance traveled, which in this case is just PQ. Okay. Right. The trouble now this just comes down to multiplication. Okay. If you know that you're applying like 20 pounds of force across 3 meters, or you have to make the units the same, like 3 feet. You can multiply them together and you get your answer. It's no big deal. The issue becomes when you're applying force at a weird angle, because we only want to know about the force that is parallel to the motion. We don't really care about any force that's going downwards. That's not going to affect the motion of the object. So instead, if you had maybe like a slab that you were pulling, and sometimes the strongmen they will do these slabs, and maybe you're pulling it at an angle. In order to figure out work, we want to know the amount of work in the direction of travel. So the guy's really going in this direction. He's not exactly getting an efficient amount of force. You want the force to be going in the same direction as the travel. So in this case, you would have to take the magnitude of the projection is basically what it'll come down to. So you have to go magnitude of the projection of whatever the vectors are. In this case, it's the force vector onto this PQ vector, and then multiply it by the distance traveled, which will be the magnitude of the PQ vector. Okay, so we can put a vector here for PQ. Okay, so it's a simple formula, but it can be made difficult by just, you're tilting the problem a little bit. Instead of pulling straight forward, you're kind of pulling at an angle, which should be the case if you were pulling a wagon or something, and that's actually the application from the book I want to look at. Anyways, the formula you'll use won't be this particular formula here I've shown you. You'll use one of the abbreviated formulas. It'll be work is equal to the dot product, or work is equal to the magnitude of force times the magnitude of this PQ vector times cosine theta, okay, the angle between the two guys. And you could get those from just doing substitutions. The magnitude of the projection is going to be F dot PQ all over the magnitude of PQ squared. And then if you multiply it times PQ, and actually the magnitude of the projection, it'll get rid of the squared part. Okay. And I won't bother you with those details, but the deal is this will cross out with this. And this should be a magnitude as well. And you'll just be left with the dot product. And of course, you could rewrite the dot product as this in this other form as well. Okay, so there's the kind of the derivation of those. It doesn't help very much, honestly. We'll just come down to memorizing. And I will give a lot of formulas on this test. So let me, after I get done with this video, I'll go and post the formula sheet for test 3. And you'll have a better idea of which formulas to use. So anyways, I'm looking at problem 56 in the book, and it's on page 793. Okay, so they're pulling a wagon by exerting a force of 25 pounds on a handle that makes an angle of 38 degrees with the horizontal. Okay, so we have this wagon, and I guess somebody is pulling on it with a force such that the magnitude of the force is 25 pounds. Okay. And then it says its handle makes an angle of 38 degrees with the horizontal. So let me edit this picture a little bit so I can reflect that. This is 38 degrees in here. This is my force vector. How much work is done in pulling the wagon 100 feet? Okay, so we're going from this point here to this point way over here. If this is P and this is Q, then the magnitude of PQ is that 100 feet. Okay. And then it just comes down to using the appropriate formula. So if you use this formula, the second formula here, as opposed to this first formula, all it is plug and chug, and you'll get your answer. So work will equal 25 times 100 times the cosine of 38 degrees. And I believe the units of work are in foot-pounds. So you just take the units of the force times the units of the distance, and that is the unit of work. Okay. So in this case, you put it into your calculator, you would get 1,970. And again, the units are foot-pounds. I've also seen it written pound-foots, believe it or not. So I'm just going with how the book does it, though. So foot-pounds. Okay. So you get your hands wet with a little bit of physics, if you like that sort of thing. If not, just please bear with me. It's used in a lot of contexts, not just in physics. You can use vectors to model a lot of different scenarios. So anyways, there's that. And that will do it for the lecture videos. The next lecture video would just be a review for the third test. And that should be about it. So we'll see you next time, and thanks for watching.